This is a lesson on limits. Limits is something you should be familiar with from a previous math course, but we are going to talk about it here. Before I give some examples, I would like to draw some graphs to get the informal idea of a limit. Here's our first graph, graph of f of x. We're going to label this very important point on the x-axis, x equals a. And we're going to talk about what is the limit as x approaches a. So what does that actually mean? So if I start out here on the x-axis and then I approach a, well, correspondingly, I will approach this point here. Likewise, if I come to the left over here and I move x approaches a, then I will move along this graph, and we see that as x approaches a, the function approaches this common y value, which I will label L. In this next drawing, I will have a very similar shape. The only difference is I'm going to put an open circle here, indicating that the function does not have a value where that circle is located. So x equals a, this is still our function f of x. Now the question is, does this one still have a limit as x approaches a? Well, as we move down, this is as x approaches a from the right, we are approaching this hole here. Even though there's not a value there, we are approaching it. And as we approach from the left, we are approaching where that hole is. So this one, even though it is not defined, even though the function is not defined at x equals a, this one does also have a limit. We will call that limit the real number L. How about this one? Does this one have a limit as x approaches a? As we move along this curve, we get closer and closer and closer and closer to this open circle. The same from the right-hand side, we get closer to the circle. So this one also has a limit L. This function is defined at a. Notice that the point is above this hole. So the function's defined at a, and the function has a limit as x approaches a, but those two values are not equal to each other. But that's not what we're discussing. We are simply discussing in this first illustration whether or not the function has a limit. In this fourth illustration, does the function f of x have a limit as x approaches a? Well, we see if we approach from the left-hand side, we approach this open circle, so we would say the limit as x approaches a from the left would equal the number L. As we approach from the right-hand side, however, the function is getting closer and closer to this real number R. And since those two respective one-sided limits do not equal each other, then we say that the limit here does not exist. The limit as x approaches a of the function f of x simply does not exist. It does not have a common limiting value. In this fifth illustration, the same concept, even though the function is defined at a, in other words, f of a is equal to L, that's fine, but the limit as we approach from the left is equal L, and the limit as we approach a, as x approaches a from the right, is equal to R. Those two limiting values are different, so the limit does not exist as x approaches a of the function f of x. In our final illustration, we see this, perhaps you see it, it's like a pink dotted line to represent an asymptote. Let's investigate this limit. As x approaches a, we will go up the curve like this, and according to these arrows, it will continue to go up without bound. As we approach from the right-hand side, same concept, the function will get bigger and bigger and bigger and bigger and bigger without bound. So a tricky question here, does the limit exist? The correct answer is that the limit as x approaches a of f of x does not exist. This limit doesn't exist. Now, someone might say, what do you mean it doesn't exist? And we could explain that as we approach from the right or approach from the left, the function grows without bound. So we oftentimes will summarize that by saying the limit as x approaches a of f of x equals, in this case, positive infinity. Now you might see that this is a deceiving symbol here, the equalities. It doesn't equal infinity. Nothing equals infinity. This is just sort of language that we use, and I'm quite frankly annoyed with the equal symbol. I would perhaps prefer to use like an arrow saying it approaches infinity, but it is in fact agreed upon to use this equal notation. So we say that the limit as x approaches a of f of x equals infinity. That tells the reader that the function grows without bound. It also tells the reader that there is no limit. Now let's take a look at some examples. The first one, we're going to find the limit as x approaches 2 of the function. The function will be 5x minus 3. Okay, that is a line if we were to graph y equals 5x minus 3. And the way we find this limit, everybody should know this, is simply plug it in. We're going to plug the 2 in for the x because we can, and this comes out to be 7. So that method is the easiest method. If you can plug it in, do plug it in, and that method is what the French call substitution. Now for our second example. This one is going to be the limit. Now all of these are in your packet if you're following along. As x approaches 1 of the function, this is going to be a rational function, x squared plus x minus 2 over x minus 1. We cannot use substitution here. We try to substitute 1 in for x, and we would see that we would be dividing by 0 in the denominator. No good. So I think you know at this point what you need to do. We're first going to factor so that we can simplify. Okay, so I'm going to rewrite this. The limit as x approaches 1, the factorization, x minus 1 times the quantity x plus 2 all over the quantity x minus 1. Okay, and then we would cancel these out. And I want to make this point here. It is not okay for this unit to cancel that out and go directly to the substitution portion. I want to see what the expression looks like after we cancel everything out. So that's just going to be left with x plus 2. Now at this point we have it simplified, and then we go back to good old-fashioned substitution, and so our answer is going to be 3. This particular expression here is needed. You must have the result after simplification. However, this step here is not needed. You don't have to show the factorization and then canceling out. You just have to show the result after it. However, most people prefer to write both of them to show all their work. Now, this method is going to be called, we get to call it whatever we want. I'm going to call it simplify and then substitution. Example number 3. In this example, we cannot directly substitute 9 in for x because we see that we would be dividing by 0. In fact, this one would be 0 over 0. That's indeterminate, but that's languages for another lesson. Anyway, we can't plug in the 9. So we're going to simplify and sub. Now, in order to simplify and sub, we need to first make an adjustment, just like factoring was an adjustment before we simplified. This one is going to have a different type of adjustment. I'm rewriting this. I'm going to encourage you to do the same. It looks like I'm just repeating the same exact thing, but we will add on to this. I want you to know the words, not just the method. What we're going to do here is use, you might recall something called a conjugate. So the denominator is radical x minus 3. The conjugate of the denominator is going to be the quantity radical x plus 3. And so what we do is multiply the top and bottom, the numerator and denominator, by the conjugate of the denominator. Let's say that again because I want you to know that language. we're going to multiply top and bottom by the conjugate of the denominator. Okay, once we do this, we're not simplifying just yet. We are going to do a little bit more adjustments here. I'm going to leave the part that is not conjugated. We're going to leave that alone, and so the numerator is going to continue to look like this. Now what I'm going to do is expand or FOIL the denominator. So we have radical x times radical x, and that comes out to be just x. Then we're going to have a minus 3 rad x plus a 3 rad x, and those two cancel out. That's the purpose of writing the conjugate. And then finally, negative 3 times a positive 3 is a negative 9. And we're left with that. We see here that we have the ability to cancel out the quantity x minus 9. And then, like I stated in the earlier example, I want you to write the result after the simplification, which is radical x plus 3. And now we're ready to substitute, and that final result is the limit is equal to 6. This example was another illustration of the simplify substitute method. I do want to point out here, some students have pointed this out to me, that the conjugate method is not the only way to make adjustments. So I'm going to redo this example. I want you to know the conjugate method because not every example is going to be able to have two ways. But I do want to point out in this one that you could actually factor this. If you factor the numerator, we will have radical x plus 3 times the quantity radical x minus 3, and then the denominator is radical x minus 3. We cancel out the quantity, and we have the limit as x approaches 9 of radical x plus 3, which equals 6, which is consistent with the other way we did it. So in this case, you can use either method, but you definitely need to be aware of the conjugate method in addition to the factoring method. Okay, we're going to take a look at example number 4. The goal of example number 4 is to find the limit as x approaches 1, period, of the function f of x. Now you will see, since this function is defined piecewise, the behavior of the function to the left is different than the behavior of the function to the right. So to the right of 1 we have a quadratic, and to the left of 1 we have a linear function. So those two behaviors are different, and because the behaviors are different on either side of 1, we need to do limits from both sides and compare them. So let's start this off. First, we're going to take the limit as x approaches 1, and we can pick from either side. I think I'll just pick from the positive side or from the right-hand side. And I will say the limit as x approaches 1 from the right of f of x. I use the generic f of x because I'm referring to the main function in question. And then after that line, I write the behavior. So this is the limit as x approaches 1 from the right of the function's behavior to the right. The behavior to the right is this quadratic x squared plus 1. So this respective one-sided limit now can be solved using substitution, and that comes out to be 2. The next thing I will do is take the limit as x approaches 1 from the left of the generic function. Please don't skip this step. Many students think, well, the whole point of this is just the answer, and they start off with writing this and forget to write this, but both of them are very important. Next, the limit as x approaches 1 from the left of f of x is equal to the limit as x approaches 1 from the left. Now the behavior to the left is 3 minus x. When I plug 1 in now via substitution, I get 2. And since these are equal to each other, and only because they're equal to each other, we can conclude by saying the limit as x approaches 1 of f of x, period, 1 period. is going to equal 2. See, the limit from the right was 2 and the limit from the left was 2. Therefore, the limit, and I'll use this therefore symbol, the limit as x approaches 1 of f of x equals 2. And this 4 up here has absolutely no influence on the limit. If you recall from the illustration, that's just a random displaced point. So maybe we'll draw a graph of this so that we can piece it all together. This is going to be a pretty crude graph, x-axis. Okay, the point in question is 1. As x approaches 1, what is the limit? So let's first do the behavior to the left. We have this linear portion, so 3 minus x, y-intercept of 3, and a slope of -1. I'll leave this as an open circle, and the function will look like this to the left of 1. Next, we're going to take a look at the quadratic. Okay, so if I were graphing this ordinarily, I'd have y-intercept of 1, and then I'd go over 1, up 1. So this one also starts with an open circle here, and then works out quadratically in this fashion. And then we have this random displaced point of 4, which is up here, but that has no influence on the limit itself. As we approach 1 from the right, the function gets closer to 2, and as we approach from the left, the function gets closer to 2. Therefore, the limit is equal to 2. Now, I would like a name for this method. We're going to call it the 2 one-sided limit theorem. Because this is a piecewise function and it has different behaviors, we need not 1 but 2 one-sided limits. So this was a one-sided limit, this was a one-sided limit, and we needed 2 of them. So we'll call this the 2 one-sided limit theorem. Now, before the lesson is over, I want to carefully define this theorem, and then you will be responsible for knowing the theorem. For right now, let's just know it by name. When you have a piecewise function, let's use the 2 one-sided limit theorem. Example number 5, f of x is the absolute value of x over x, and the goal is to find the limit as x approaches 0 of this function f of x. So we have this absolute value. We first always check the substitution. Can we substitute? No, you can't substitute. You get 0 over 0. Can we maybe simplify? Well, I don't see any factoring or conjugate, so that's not going to make it any easier before we substitute. So wait a minute, in the last unit we talked about turning absolute value into piecewise functions, so let's do that. And so the numerator is just going to be regular x and then over x, and that's going to be provided that x is greater than 0, and the numerator will be the opposite of x over regular x, provided that x is less than 0, and in this case x cannot equal 0 because we'd be dividing by 0. Anyway, I'm going to simplify this like we did in the last unit, and so f of x is going to equal 1 provided that x is greater than 0, and then f of x is going to be -1 provided that x is less than 0. So before we graph this, I want to approach it very systematically using the algebra, and we have a piecewise function and the behavior is different on both sides of 0, so we need 2 one-sided limits. The first one here, I'll just put a little box to start us off. We're going to take the limit as x approaches, again you get to choose, I'm going to choose from the positive side first, of our function f of x. Remember, I'm going to write the generic function of the one in question before indicating the behavior. See, I think all of these are really easy to find limits, and it's not about answers. It's about communicating your answer in a sophisticated manner, and so we will do that. And so now we follow by the limit as x approaches 0 from the right of the behavior to the right, and it looks like the behavior to the right is just good old-fashioned the number 1. Now we take the limit of a constant, and since this function is not varying in y, the limit of a constant is just the constant 1. Now we'll do the next limit. the next one-sided, that is, the limit as x approaches 0 from the left of f of x equals the limit as x approaches 0 from the left. The behavior to the left is -1. Limit of a constant is the constant. Ooh, these are different. From the right it equals 1. From the left it equals -1. And our two one-sided limit theorem will tell us when they are different, the function does not have a limit. And so, therefore, the limit as x approaches 0 of f of x, period, does not exist. If you wanted to give the reader more information why it doesn't exist, well, you would give them this information above. But the final concluding statement is that the limit does not exist. Example number 6. Let's go through our methods. I always start off, can I substitute? I want to find the limit as x goes to 0. Can I plug in 0? No, I cannot, because I'd have 1 over 0, and that's not allowed. So, substitution's out. Can I simplify it? Well, you might work with this, and you would realize pretty quickly that there's no simplification to be had here. How about piecewise function? Well, no, it's not a piecewise function at all, nor can I write it as one. Oh boy. So this is going to require another method, and you might know this by a different name than I'm going to use it, and you're free to use that name, or you can use the name that I employ. But before we do that, I want to get to a little bit of theory to explain this method. So hold on tight for this. Okay, picture you have, I like to talk about a sandwich, and the sandwich has two buns. You have the top bun and the bottom bun. And so picture one function, the top bun of the sandwich does this, and the other bun, the bottom bun, does this. Okay? And suppose we knew that the red bun or the top bun goes to 0 as x approaches 0, and same with the bottom bun. The green goes to 0 as x goes to 0, so that's fine. Then if I had a sandwich, the contents of the sandwich that go in between the buns, let's say that did this. Well, we knew that the red went to 0, and we knew that the green went to 0, and if we also knew that the white was always between the red and the green, then we could logically conclude that the white also goes to 0. So that's the logic behind the sandwich theorem. That's the term I like to use, sandwich theorem. Other authors will call this the squeeze theorem, so you might know it by one or the other. So let's do this. All right. The first thing we need to accomplish is identifying the buns. So this f of x is going to be our contents of the sandwich. And we need to make sure that we have another function that's always bigger than that, and a different function that is always smaller than that, or beneath it, if you will. Here's how I'd like to start. Now, most of these are trigonometric functions that do go, in fact, to 0. Let's say the sign of smiley face. Now, the reason I'm using some generic smiley face, because smiley face can be anything. Here's how the limit is found in the work that you would show. The sign of smiley face. Well, no matter what smiley face is, at the absolute biggest, no matter what smiley face is, we know that the sign is always less than or equal to 1. We also know that the sign of whatever is always bigger than or equal to -1. So that's a given statement about the sign function. Now, that's not what we have as smiley face. We actually have 1 over x squared. It doesn't matter what that is. We still say that that is between -1 and 1, like I've shown here. That's a real nice inequality that we have, but that is not the contents of our sandwich. The contents of our sandwich is what we have circled here. So what we want is x squared sine of 1 over x squared. That's what we want. So how did I go from this purple portion here to here? Well, I multiplied by x squared. So if I multiply all sides by x squared, 1 times x squared is x squared. Negative 1 times x squared is negative x squared. So I just multiplied all sides by the same quantity, and so now I have this inequality. And this is very desirable because I have the contents of my sandwich. I also now have the upper bun. I maybe should have used the red here. I have the upper bun. And I also have the lower bun. So I have a successful sandwich. That's not enough. We have to now go on to say, well, the limit as x approaches 0 of my upper bun function, x squared, well, by substitution, that is going to equal 0. I also have to talk about the lower bun and say the limit as x approaches 0 of negative x squared, that also goes to 0. We have what we need. We have a successful inequality sandwich. We have that the upper bun goes to 0. We have that the lower bun goes to 0. And then all this information together will conclude that the limit as x approaches 0 of the contents of our sandwich also goes to 0. And just because I worded it initially as f of x, I'm going to finish off by saying the limit as x approaches 0 of f of x equals 0. And that's called the sandwich theorem. Okay, now let's take a look at example 7. A little bit different here. This time we're going to talk about some properties of limits. Up front, these two different limits are given. This is not true in every single case. It's just like an example where you could say the limit as x goes to 5 of f of x equals 0, and suppose that it is also known that the limit as x approaches 5 of a different function, g of x, is equal to negative 2. So that's like the given information of this particular problem. And then we're going to use that given information together with some properties to find some limits. Let's start with part A. The limit is x goes to 0 of f of x plus g of x. The idea here is since 0 is a real number and negative 2 is a real number, both of these limits exist. And if both limits exist, then you can employ some properties. One is the limit of a sum is the sum of limits. So I will show here the limit as x approaches 0 of f of x plus the limit as x approaches 0 of g of x. The limit of a sum is sum of limits. And then we just plug in what we know. So the first property says that this is equal to 0. The second property tells us this is negative 2. And so the limit is negative 2. The point here is not to say, oh, it's hard to find the limit. The point is to show the properties. Again, if both limits exist, then we have these properties. The limit, oh, actually, let me have you think this out loud. I know you're talking to a computer, but if part A was the limit of a sum is sum of limits, what would part B be in words? How would you say this property? The limit of a product is the product of limits, provided that each exist, of course. Okay, times the limit as x approaches 0 of g of x. And then we're back to substituting based on the given information, and that limit comes out to be 0. Okay, the next one. The reason I'm showing this one here, part C, is we apply really the limit to the functional part. Let me kind of go over here to the side to explain it. Suppose I had the limit as x approaches 1 of 5x plus 2. What we could in fact do is say 5 times the limit as x approaches 1 of the x plus 2. See, what I've done is applied this limit to the only part that can vary, the functional part, And so I write it like this, and then that comes out to be 5 times 1 plus 2, which is 7. Answer's not important. The idea here, though, is that the limit can be applied to the functional part only. So e is a real number, 2.718 dot dot dot. It's supposed to represent a real number. And so what I'm going to write here is this is going to be e, and then I'm applying the limit to only the functional part. So I'm applying the limit only to the g of x. And now I have this property that stands out, and I know the answer to this portion. So this is going to be e to the power of negative 2. Sweet. I guess we could also write that as 1 over e squared. Okay, the same idea is going to apply in part D. I'm going to apply the limit to the functional part. So what would this look like? Well, it's the limit as x goes to 5 of the cube root of f of x plus 27. Now I'm going to say the cubed root of the limit as x approaches 5 of f of x, and then plus 27, so that I have that property staring me in the face, and now I can substitute its answer, and so now we have the cubed root of 0 plus 27, or simply the cubed root of 27, which you should know is 3. We'll call that method properties. This is less of a method than it is just using properties. Okay, so let's move on now to example 8, and this is the limit as x goes to 0 of the sine of x over x. All right, let's run through our list of things we might be able to do. Number 1, can we substitute? No, you can't divide by 0. Is there a way to simplify this? No, you cannot. The third method, is this a piecewise function? No, it's not. Oh, how about the sandwich theorem? Well, there'd be some temptation to work this one out with the sandwich theorem, but it turns out it doesn't work. No properties into play here. So I want you to think of what else you could do. Now, if we were in class, this is a little easier. People would raise their hand, and I would ask, and some common answers would be, use your calculator. Okay, fine. What do you mean, use your calculator? And some people mean maybe graph it. Great. That is a great way to try to find this limit. Graph it and figure out if there's a value that it's getting close to, such as we did in the warm-up illustration. Another thing people might say is plug in numbers close to 0. Keep plugging in closer and closer and closer to 0 and see if it converges to some limit. We would call that more of a numeric analysis, and those are absolutely great, great, great answers. The point I want to make here, though, is without those graphing calculators, there are going to be some limits that you just flat out have to memorize, and this is one of them. If you were to graph this, you would find that the answer is 1. I simply want you to memorize this. Memorize. So you'll need to know this on the test. Okay, example number 9. We're going to switch gears here a little bit. Let's find the limit as x approaches 0 of 1 over x. From the last unit, you would recognize the function y equals 1 over x as a rational function. But I'm going to just do some numeric analysis. I'm going to approach this from the right and from the left just to get a sense of what's going on here. So we're going to approach limit as x goes to 0 from the right of 1 over x. All right, so the top of this thing is always positive, so that doesn't change. Now, if we get closer and closer and closer and closer to 0, then the denominator is going to be really, 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 really small, but it's also going to be positive because we're approaching from the right of 0. So if you have some positive number and then the denominator gets small, 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 very, 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 very small, that means this number here is going to get really, really big, because when you divide by really small, the number gets really big. And if this gets almost practically 0, then this fraction is going to approach positive infinity. If we take a look and investigate from the left, the limit as x approaches 0 from the left of 1 over x, we can do a similar analysis. The top is always going to be positive, and if we get close to 0, then the bottom is going to be really small, but it's going to be negative. And so what is this going to? Well, forget about the negative for a minute. Any number divided by something extremely small is going to continue to get larger and larger and larger, and that's the infinity concept. But now, because of the negative, it's going to approach negative infinity. So this fraction actually gets smaller, not in magnitude, but in negative value, gets more and more and more and more negative. So we would say approaches negative infinity. If I put these two together, which we sort of talked about this, the limit as x approaches 0, period of 1 over x, does not exist. And that's the traditional does not exist. If you wanted to tell the story more, you would give more information, and this information would let the reader know why it doesn't exist. It grows without bound in one direction, it gets smaller without bound in the other direction, and therefore the limit doesn't exist. Again, I can't repeat enough, the best way to do this limit would be your knowledge of a graph, and so the graph of 1 over x looks like this, and then also looks like this, depending on where we're at, and we see that as we approach 0, as x approaches 0, the function limit does not exist. Okay, let's take a look at number 10. In number 10, we're trying to find limit as x approaches 2 of 1 over quantity x minus 2 squared. In a similar fashion, we're going to investigate from two different sides. So the limit as x approaches 2 from the right, 1 over x minus 2 squared. Let's do our numeric analysis. The top is going to be positive. The bottom is going to be really, really, really small. And even if you take something really small and you square it, it makes the denominator positive. So you have positive over a really, 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 really small positive. That means we're going to approach positive infinity. Okie dokie. And so the limit from the left-hand side, the limit as x approaches 2 from the left, 1 over x minus 2 squared. The numerator is going to be positive, and the denominator is really small. And we're squaring it again, so that's also going to be really small positive, and so we're going to approach positive infinity. We put this together and say the limit as x approaches 2 of the function x minus 2 squared. And I've made this point now a couple times. I want to make sure it's crystal clear. This limit does not exist. It doesn't exist. It doesn't exist. It doesn't exist. Why the heck then would we say equals infinity? We only say it equals infinity because from the right it grew without bound, and from the left it grew without bound, and so period, this thing grows without bound, and we summarize it by saying it equals infinity or positive infinity. It would not be wrong to say that this limit does not exist. As a general rule, we want to be as specific to the reader as we can, so we summarize it by saying equals infinity. And here's a graph. On the last page of notes for this lesson, you will see a kind of outline, and I'm just going to walk through the outline, not to beat a dead horse, which, by the way, is the worst expression you can ever say. Anyway, number 1, substitution. Pretty straightforward. Simplify sub. 2, one-sided limit theorem. That's again when we have a piecewise function. We have the sandwich theorem, also called the squeeze theorem. We have properties, and then I kind of clump a bunch together. Either you're going to memorize it, or you have to resort to some numeric analysis or some graphic analysis. So that's the 6th method. All right, let's finish up this lesson by defining a couple things. We have a definition of a vertical asymptote, and the definition will read as follows. The line x equals a is a vertical asymptote of the graph of a function y equals f of x if And then we have these statements. This should be familiar to you from the last unit. The limit as x approaches a from the right of f of x equals plus or negative infinity. Or you could have an asymptote if the limit as x approaches a from the left of f of x equals positive or negative infinity. Or both, of course. So that should not be new to you, the definition of a vertical asymptote. Okay, as promised, let's formalize the two one-sided limit theorem. This says the limit as x approaches a of f of x will equal some real number L if and only if the limit as x approaches a from the right of f of x equals L, and the limit as x approaches a from the left of f of x also equals that number L, that real number L. And that is the theorem.